So there you go. Okay. So the general impression is that there is a smaller set of, let's say, characteristic people or shoppers or movie watchers, rather than the full space, which would be the total number of viewers that are out there. So if you're Netflix, you're saying that I don't need or I don't expect that every single viewer is different. Although there might be, but fundamentally you can group them together. So in terms of the key characteristics, you can minimize it. You can do the same thing for your items as well. So overall, we can represent our large matrix by a smaller subset, okay? A smaller approximation. This is not going to match exactly, but it's going to approach it very closely. And that's why we talked about that if we have this n by n matrix, one option would be to represent it by two sort of skinny matrices. So let's say that there are d different classes of viewers and there are d different classes of users, and that's what matters really. So we would represent the matrix M as a product of these two very long rectangular matrices. U is going to be n times d, and V is going to be d times n. And this basically gives us these two skinny, dense matrices, and their product is going to give us the full matrix M, right? So what we would like to do is to approximate UV. Now try to think of why you would want to do it. Actually, wait a minute, I'll explain exactly why you want to do something like this rather than fully estimating all the entries of M. If we are able to do this kind of a decomposition, which means that we had some entries in M that we know about, and there are a lot of missing entries, so we could use those entries to figure out what U and V are. Look in terms of the number of variables. Let's think in terms of variables, right? M is of size nm, correct? Whereas if I'm storing U and V, then it is it's basically n times d plus d times m. Now if you make an assumption that d is significantly smaller than n and m, then we have fewer unknowns that we are representing. And so this is, in one way of looking at it is that instead of knowing n cross m unknowns, which will be basically the utility values for every single item that every single user could potentially be interested in, we're saying that we have this sparser representation which will characterize it. And D is sort of a measure of how many or how complicated that these categories are. Okay?
You take out the sigma.
This I'm not talking about singular value decomposition yet. I'm talking of a simpler way of doing this. It is eventually related. So for those of you who did read about it in the singular value decomposition, you're going to have sigma out here. So I'm going for a more ad hoc approach right now. We'll get to the formal singular value decomposition later. Okay? This is something which is sort of leading up to it. So one way of looking at it is that UV is still going to be an approximation, right? It's not exactly the same as M. So what we want to do is that the product of U and V is going to give me another matrix, let's say P, which is going to be somewhat equal to M. Its entries are. And what I want to do is to define a measure just the same way as we were doing earlier. It's a similarity or a distance, which says how close is this product to the matrix that we are actually interested in, M in this case. And so you will basically, the most common way of doing this is to use like a root mean square error, which is the square root of the sum of differences of, importantly here, you need to mention that this is only the non-blank entries. So if we don't know the value of an entry in the utility matrix, we do not use that to compute this similarity. Okay? Is that clear? So I'm saying that wherever an entry exists in M, the product of U and V, the corresponding entry, should be as close to it as possible, right? And wherever I don't know, that's where I'm going to use this eventually to predict it.
If you predict it from UV.
Yeah. So think in terms of what we want to do, right? We want to, actually, let's ignore this part as well, I'm sorry. Let's go here. Yeah. So the key part is that we want to estimate these two matrices U and V using partial values of M, right? If you think of this product that we will define U and V, between U and V, you can think of it as a set of equations written with these entries. So the unknowns that we are interested in are the entries of these matrices U and V. If we choose a small enough D, we have fewer number of unknowns. And ideally, in some sense, what you want to make sure is that the number of filled entries in M, which is the non-blank entries, are at least as much as, or somewhere approximating the number of entries that we have, which is N times D plus D times M. And so that's what we are trying to solve, right? And here we have assumed what the space is. If you think of the other approach that we talked about last time, as the matrix N becomes larger and larger, the percentage of entries that you actually have information about becomes smaller and smaller, right? Think in terms from you can prove it mathematically, but fundamentally think of it that there are more and more items that you can buy, say, from Amazon or something. But the number of items that you have rated or you actually consider is more or less remaining constant or not growing at the same rate. And the same is true for all the number of users who are increasing. So you're getting to a larger and larger matrix with fewer and fewer entries. So those approaches do not scale as well. What you're trying to say is, instead now with this sort of an approach, is that the rank of the overall matrix is not really changing at the same rate. So even if the sizes are increasing, I can still approximate it by D, or even if I add, say, a few thousand users or a few thousand items, maybe I need to increment D only by 1 or 2 to actually accommodate this, right? And so that's sort of the general intuitive idea behind doing something like this. We talked about normalization, and this is mainly because of how we are comparing across this. We're going to try to characterize all users instead of saying individual users and individual items. We're trying to get a sort of a cumulative model for this, right? The D sort of represents what this common model for all of this is. So we need to normalize. I talked about this. We need to normalize between the users by subtracting the average user rating. We need to normalize for an item by subtracting the average item rating from the. Of course, when we are setting up the whole matrix, you might want to do both, in which case you basically subtract the average of the user and item rating from a particular entry. So you'll have every row and column intersecting at a point. You take their averages and you subtract them. And when we actually eventually end up making, so we can start, so we have a way of measuring how good this product of U and V is with regards to M. That's a cost function or an objective function that we want to minimize. We want to make it as small as possible, which means I want to bring these two as close as possible. So you need to start with a good guess because it's a very ill-posed problem. In general, you're going to have more entries in U and V than maybe we have the data. Or because the way we are trying to predict it with using only a subset of the values of M, there might be multiple solutions which all sort of minimize it, which in terms of our objective function means that you might end up with a local minima as opposed to a global minima, right? In order to counter that, using some amount of randomness works. So you try to use something which is a reasonable guess. If we have normalized the ratings, then a 0 is a good guess because that's sort of the steady state version, and then minor variations are going to specify whether you like it or you do not like something. The randomness helps because we can start with multiple guesses, and as we optimize it, we're going to try to approach the solution. And if your solution is a true global maxima, then most of these will try to converge to the same level. We've defined a function, right? So if you think back of your basic calculus, yes?
So the way you're planning to do it is you're converging, right? And you might, if there are a lot of enough small buckets in your function, then you might not come to a global minimum, right?
You won't, and this is a hard problem. So in general, you can't really do a very good job of solving it, okay? But let's think of it. You think of your basic calculus lecture. So let's say we have a function. Here in this case, we have a function which is measuring how close uv, the product uv, is to m, right? And it's a function of unknowns, which are the entries of u and v together, right? So we have a function, and we want to minimize it. So I'm assuming all of you know this, but let's just go over it again. How do you actually find the minima of a function? So that's why this is nonsense. Okay, so you want to compute the gradient of it, because the gradient is going to be 0 at the extrema, the minima and the maxima, right? In this case, because of the computational cost of computing the gradient, we're not going to go for the second order optimality condition, which is to use the second derivative, because it's going to be very expensive. We're only going to use the first order optimality conditions, okay? And we are going to do it in a slightly different fashion. So I'll work the math out, but fundamentally that's what we are using. If you have an arbitrary function, right, the general idea behind gradient descent, and we're going to look at some variants of this, is that I want to end up at the minima, right? So if I'm at a particular location, and we have a function, let's say like this, right? What does the gradient tell me? The slope, which means that if you are at a particular location, you are at a particular guess, and you want to end up at the minima, which direction should you go in? Yes, so you go against the gradient. So this is like also called steepest descent. So that's the best guess for you to go, because you're sort of searching in a space. Imagine you're somewhere and you want to find the deepest point in the valley or something. Your best bet, there are better ways to do it, but one of the basic ideas, if you go by a first order optimality, is to go in the direction, in the negative direction of the gradient, right? Because that takes you. Conversely, if you were to want to find the maxima, then you would go in the direction of the gradient itself, okay? And so that's sort of the general idea behind it. It's a first order approximation. And again, this general idea is that you would go proportional to the negative gradient. Now, you don't want to go exactly, you want to scale it. You want to take a step in that direction, because in the most general case, you don't know how far you want to go before the gradient changes again, right? So you're going to take a step which is scaled by some factor, and we'll look at how you would get this thing. And once the gradient is 0, that's our optimality condition, so we can stop. So this is an iterative way of taking steps, always looking at the gradient, trying to get to the minima whenever we can. It is very, very inefficient for large matrices. Why is it inefficient for large matrices?
You will get only local minimas.
You will only get local minimas in this case. So this is not going to. So this is very, very sensitive to your initial guess. So it's not going to give you the global. In these kind of problems, which are very ill-posed and the objective function is not really convex, it's a very, very hard problem to actually get the global minimum. And there are a lot of heuristic approaches to avoid it. But let's skip that. For those of you who are interested, we can look at some of these approaches for your project or something. Okay? We're going to talk about two ways of handling this. The reason why it's large is twofold, right? One is that the number of unknowns is very large. So, right, so u and v are still functions of m and n. We have sort of reduced it. So let's just assume that we are talking of a square matrix for now. So the original matrix is n squared. So we had an n square matrix, and we have sort of converted into 2nd. So we've reduced the size, but n is still very large, to the order of millions or billions, right? That's how large are the variables that we have to estimate. Our unknowns are so much. So these are really large. The gradient, right? The size of the gradient, the size of our unknown vector and corresponding the size of the gradient vector is going to be 2nd long, right? So computing this gradient is expensive, right? Updating all of this. So you have two approaches. One, which is sort of like a simplified version of the stochastic gradient descent, which I'll present now, is to say that I'm going to look at one particular entry between u and v, and I'm going to estimate the best value for that, go on to the next, estimate it, and so on. But even this is very, very inefficient because you're going to access the data at every single point. So let's actually look at gradient descent. So we already talked about it. If you have a function, then the minimizer is basically by going in the negative direction of the gradient. And for some sufficiently small, in our case, we are basically minimizing this. Is this clear? We're minimizing the difference between m and uv. Only difference being this is mathematically incorrect because we're only comparing this term wherever m is non-blank. Okay? This expression out here, we are updating one entry at a time, right? How much is look at the amount of data that we are reading in, or the data dependency is still pretty high, right? We need access to an entire row of m, yes?
If you're updating one one VS or one X, then only after we update it, then we move to the next element, or can we update parallelly multiple?
Depends on that. There is a dependency here, right?
Okay.
So you could come up with those strategies. I'm not saying that you cannot. In this particular case, you're not, because there are other challenges with that. And actually, one way of doing this in some ways would be to actually use something like coloring to break the dependencies. So you will say that I'm going to update one color at a time, because you're reading all of these values, and if I'm going to update this guy, if I had another one reading differently, they would get updated independent of each other. So you need to sort of break a tie at some case. But the bigger problem here is that in order to update this one particular value, I'm reading a lot of data from U, V, and M, right? And I'm doing it again and again and again. So if you were to, let's say, implement this in a map-reduced sort of fashion, the amount of work I do, the amount of data that I read is too much for the amount of actual update. I'm doing one update, but let's ignore U and V for now, assume that they fit into main memory. But at the very least, I'm reading an entire row of M every single time, right? So the main motivation for stochastic gradient descent is to actually sort of flip the problem on its head and say instead that let's see if we can drive it from a single data point. So it's much more common in the machine learning community, and it's driven by the fact that each entry of a matrix M, the non-blank entries of M, right? Think of it as a training sample. It's a piece of information that I have that they're coupled to a row and a column of U and V. But let's look at it the other way around, which is that given an entry of matrix M, can I update the row and the column of U and V that depend on this? Okay? So you're looking at it the other way. Now you can think instead that maybe we don't even need, if our assumption on the low rank of M is true, then maybe even the few non-blank entries that I had, I don't even have to look at all of them. I would instead start saying that, start with a guess, get an entry from M, update the rows and columns that dependent on it, and move on, get another sample. And this way, at some point where U and V start converging to according to some norm, then you can stop. I don't even need to look at any more entries of M. All of this assuming that it was indeed low rank. Is it clear? At least intuitively, is it clear the way the approaches are different? Right? So it's driven by data. And for it to work, you want to be able to break down the objective function in terms of the local cost, where local cost here corresponds to each particular non-blank entry of M. So if this was my cost, W being the unknowns, which would be all the entries of U and V, we can break it down depending on the number of data points that I have. These N here would be the non-blank entries of M. I'm breaking it out into local costs, the way the cost is affected by a single entry of M. In our case, I'm summing over ij's. Ij is such that Mij is not blank. And the cost is now going to be defined by Mij, the corresponding row of U and the column of V. Is this clear?
But some of the MIJs might start getting non-blank because of the data which is coming in, right?
No. So M, you're given some
you
M.
already have it.
So I didn't write it here, but say that ij such that mij not equal to is known. So I have,
Oh, sorry, I think
think from the
I thought
data
you were also
perspective.
constructing
Start from the, so this is ij such that
I think my question is, are you constructing M or you already constructed M? And
M
then
is
you only
M is
use
your input, right?
UNV?
M in both cases, M is your input. This is the matrix. So, okay, take a step back, right? We are sort of doing it in a two-stage. So we start with a M which is incomplete. We go to UV which are dense matrices, and using those I can predict the other entries of M.
Yes.
So M is in some sense both the input and the output, but let's forget the output. We are only concerned about going from this M, which is partially known, to this sparse representation using the skinny matrices U and V.
Then go back to
Right? Understand this, because this is sort of it's important why you need to look at the problem differently. When the data becomes really large, you want it to the data to drive it rather
question
than
is, if I have like data coming in, do I take a set of data, construct M, and then do UV, and then go back, update
you
M?
need to explicitly construct M. Especially if you go for this sort of an approach. I get what is an entry ij. Let's say that you decided to go right now and rate a movie on Netflix. That is one MIJ. So the moment
But
you
the
do-
data is in C, right? But the data is still, I've not read the data, right? How do I know MIJ, which MIJ is full or not? That
No,
user
so
data-
this boils down to the format. So you're going to be storing M in a sparse format anyway, which means that I'm not storing the entries which are, so you did this for your graphs as well, right?
So in some sense, I've read all my data, constructed M, and then started null.
We'll get to the practical aspects of this data, but actually it'll be clear to you in a couple of minutes. But that's what I'm saying, even though you might be reading it from file, think of it more from the online learning type of perspective, which is that you went and clicked on a rating right now. I have a single entry. Can I use this now? This only affects the one row and a column of U and V.
Okay.
So let me go and update that because this data has been brought in, right? So think of it that somehow we're bringing in one data point at a time, and this is like typically called data assimilation, right? You're bringing in data and I'm updating my model in an online fashion, right? Is it clear? And we'll see that this also exposes some levels of parallelism because of how we are doing this. So what is more important to realize is that we can now write our cost in terms of this. This is the way I would write my cost, and I'll expand this out for you now. In terms of the single entry in our utility matrix and how it depends on U and V. Okay? Understand this. This is important because in a traditional gradient descent, this is what we would do, right? We update our values going in the negative direction scaled by some value, summing over all our individual gradients for all the data points, right? We consider all the data together. Because the structure of a problem, maybe some of them disappeared, like in our original case, we only considered one particular row or a column of M, but this is the general. In stochastic gradient descent, we are not really getting the gradient, we're just approximating the true gradient using a single example. So that's why we are saying the structure is exactly the same, but now instead of using the summation of all the data points, the effect of all data points on the gradient, I'm going to only say that what is the gradient if I only consider one data sample. Okay? This is an approximation. Here again, similar to the arguments I made earlier, this is not as accurate, it is noisy, but it is super cheap. So here you are saying that I might take more steps to reach the optimum, but it's going to be so much faster, right? So there is a trade-off between the cost of computing the gradient and how good that estimate of gradient is. So that's the fundamental idea, but now let's see how we can formalize this. What do you think? We're almost out of time, so I'm going to get to SVD the next time. But what is the issue with this particular algorithm here?
What is the data comes in with influence is completely different, right?
Yes, in general, that goes again. So we've sort of made the assumption that it's not really changed. So you are, as you bring in more and more data. So fundamentally, one other issue that I should talk about here is that this lambda, you're going to start off with a large step size. And as the iteration progresses, as you start converging, you're going to keep reducing that. So in a dynamic fashion. So there are a lot of factors and parameters to adjust out here. But in general, this is going to start, so that a lot of people in the machine learning side will call that the learning rate, which you're dynamically adjusting as you get closer to the solution. But this is going to converge. And it's depending on the data, right? So what you will see is that that's why you want to uniformly sample it. If you did not uniformly sample it, you're going to change all over the place as you're moving, right? If all your data was coming, let's say that you instead decided to go with one user, right? So if you started from just one user or one particular item, then you're getting a strong bias and you're moving in that direction. But as long as you have, in the early stage at least, you started with a fairly uniform sampling of your entries, this should start converging pretty quickly to a reasonable approximation for U and V. Okay? And now we have basically broken down you can do something a little bit in between the two approaches, which would be sort of like a batch case. So here's, instead of saying that I'm going to look at only one data point at a time, this sort of goes into our arguments when we're looking at MapReduce and the using of groups. We can say that I'm going to treat a bunch of IJs, so think of a block in a fashion, and I'm going to do those in the traditional gradient descent fashion. But across, in the parallel sense, I'm going to do them broken up in a stochastic fashion. So instead of considering one data point at a single time, I'm going to consider a bunch of them together. And the treatment for those would then be in the traditional sense, because now I'm considering a smaller number, which means that I can compute their gradients, right? So here, the gradient is depending only on one data point. You can instead say now that my gradient is going to depend. It's going to be more expensive, but there is a trade-off, right? So that's sort of where you would bring in concepts of parallelization as well, which is that you independently start.
What would you buy by getting, instead of one data set, a few more data sets?
So you're basically balancing out the fact that if I'm only bringing this, it's too cheap. I'm still, as I iterate through this, I have a lot of synchronization. So you're not doing enough work and you're wasting too much time in synchronization. So you want to balance that out and say that, yes, I agree that it's expensive to compute the gradient,
but I have the power to compute.
I have the power to compute something in between. So you choose a size where, so these are very noisy estimates. So you're effectively saying that, let me actually get a slightly less noisy. So you're getting more data points, which means that your estimate of the gradient is a little bit less noisy than just having one single data point. And you're trading off in that sense. So you're balancing these two aspects. Okay? Why don't you all work out the expression for computing the gradient for a row and a column for this particular sort of a cost function? It should be fairly straightforward. You can assume, actually you don't need to actually, just work it out. I'll do it in class otherwise next time.